Good morning, students. Today we are going to discuss about AC generator. Okay, students. Before that, one example problem. Okay, the problem is 4.15. Okay, students. Okay, see the problem. A rectangular coil of area 70 centimeters square having 600 turns rotate about an axis perpendicular perpendicular to the magnetic field B 0.4 Weber meter power minus 2. Okay, so rectangular coil, just imagine rectangular coil. Okay, right. And if the coil complete 500 revolutions in a minute, so 1 minute the coil complete 500 rounds, right? That is the revolution. Okay, calculate the instantaneous EMF when the plane of the coil is, one is perpendicular to the field, another one is parallel to the field and inclined at 60 degree with the field. Okay, so they are comparing with the magnetic field. So when the coil parallel, the plane of the coil is parallel to magnetic field, perpendicular to magnetic field at particular angle. So we have to find out which one. EMF, instantaneous EMF. Okay, students. Okay, right. See this from the question. The data is A, area which is equal to 70 into 10 power minus 4 meter square, and N, number of turns is 600 turns, total number of turns, right? And magnetic field is 0.4 Weber meter per minus 2. Here F is the frequency. Yes, that is 500 revolutions per second now. So number of revolutions per second is the frequency. Therefore, F is equal to 500 RPM, revolutions per minute. RPM is nothing but revolutions per minute. Okay, right, right. Now come to the EMF, instantaneous EMF. See, this instantaneous EMF is, this is the formula for instantaneous EMF. E is the EMF, M for magnetic field. Therefore, E is equal to EM into sine omega t. It is nothing but sine theta, right? Theta is nothing but omega t. Theta is angular displacement, right? So EM is into sine omega t, right? So from from the EMF, which EMF is EMF in a magnetic field formula. E is EM, which is equal to N pi M into omega. Yes, pi is the flux changes, it produces the induced EMF. Therefore, EM is equal to N is the number of turns, N pi into angular velocity. Yes, we know that flux is nothing but BA cos theta. Please remember the formula, BA cos theta, and cos theta is equal to 0 degree. Therefore, the magnitude of flux BA only. Therefore, instead of pi m magnetic flux, the magnitude of magnetic flux is BA. Therefore, N into BA. Omega is nothing but what? Angular velocity. Angular velocity, right? Okay, if you are taking that frequency, yes, frequency is nothing but 2 pi by omega, 2 pi by omega, right? So 2 pi is nothing but 360 degree, because the coil rotates 360 degree now. That's why, yes, 2 pi. Okay, 2 pi by omega. Therefore, omega is equal to 2 pi into F. So that is this value 2 pi f. Okay student, that is what omega value. So therefore em is equal to n ba 2 pi f, right? So therefore please substitute the value em into this one. E is equal to nba into 2 pi f into sine omega t into sine omega t. Okay students, right? Okay, and now for first condition, when the coil is perpendicular to the magnetic field. So in the question, when the coil is plane of the coil is perpendicular to the magnetic field, what is the induced EMF? That is instantaneous EMF. Okay, so when the coil is perpendicular, what is the angle? Yes, coil is perpendicular, that is 0 degree, right? So theta is equal to 0, therefore omega t is equal to theta. So therefore omega t is equal to 0 degree. If the omega t is equal to 0, yes, please substitute the value sine 0. What is sine 0? Sine 0, 0. Therefore if this sine 0 value in substitute in this formula, so nba into 2 pi f into 0, so anything into 0 you will get 0. That's why E is equal to here 0. Okay students, because anything into 0, 0. Therefore when the coil is perpendicular to the magnetic field, yes, there is no instantaneous EMF, that is EMF is 0. Okay students, right? Now come to the second yes condition. What is second condition? When the coil is parallel to the magnetic field, the plane of the coil is parallel to magnetic field, so then that time the theta is 90 degree. Therefore omega t which is equal to 90 degree. So 90 degree value substituting in this previous formula, this formula, sine 90 is equal to 1. Therefore em into sine 90, em value nba into 2 pi f into sine 91. So n value is 600, b value is 0.4, and a value is 70 into 10 power minus 4, because centimeter square, no, that's why here is 10 power minus 2, 10 power minus 2, 10 power minus 4, right? And okay, into 2 into 22 by 7 pi value, or otherwise you will take 3.14, both are same. Okay, into f. What is f? Revolutions per second, sir, per minute. So therefore 1 minute, how many seconds? 60 seconds. Therefore revolutions is 500 divided by 60. 60 is the seconds for 1 minute. Okay, okay students, so now we will simplify 600 into 70 into 2. For example, this one we cancel, this one 60 into 2, right? 30. So divide again, cancel, you will get that this one, and 600 into 70 and divide by 7 to 22. So if you simplify these values, you will get 88. You will get 88. So 88 volt. So 88 volt is the EMF. 88 volt is the EMF. Okay students, right? Okay, right. And next, last condition is when the coil is inclined at 60 degree, right? So therefore if the coil position is 60 degree, therefore we have to is find out that angle. Therefore if when omega t is equal to, right, sine 90, sorry, 90 minus 60, because the coil is inclined 60 degree angle, that's why I am taking 90 degree minus 60 degree, you will get 30. You get what? 30. Okay, students. Therefore, theta is 30 degree, and substitute the theta value in equation is equal to Em into sine 30. What is sine 30? 1 by 2. Here, what is Em value? We calculated now. See this Em value. Em value, these values is nothing but 1. So this value NBA into 2 pi of value 88. So 88 into 1, 88. So this value is nothing but 88. Therefore, I am taking Em value 88. 88 into 1 by 2. So therefore 2, 88 cancel, 44. So 44 volt is the EMF, instantaneous EMF. Okay, students, right? Do you understand? Okay, right. Any doubt? It is easy now. So based on the orientation of the coil topic, this problem based on orientation of coil in an uniform magnetic field. Okay, students, right? Okay, shall we go to the next topic? Right. The next topic is AC generator. Which one? AC generator. Okay, students, right. See the introduction of AC generator. AC generator or alternator is an energy conversion device. Which device? Energy conversion device. It converts mechanical energy used to rotate the coil or field magnet into electrical energy. So AC generator is a device. It convert mechanical energy into electrical energy. Mechanical energy into electrical energy, right? At the same time, alternator produces a large scale electrical power for use in homes and industries, right? Alternator is a nothing but what? Generator. Alternator, both are same. Okay, now AC generator and its components are shown in the figure. Now we're going to the component. Yes, the AC generator has few components. Yes, okay, right. Before that, we are going to see about principles of AC generator. Okay, so what is the principle of used in AC generator? See, we already know the principle, induced EMF. Okay, see this one. It is based on the principle of electromagnetic induction. So what is the principle? Electromagnetic induction. And whenever amount of magnetic flux linked with the coil changes, an EMF is induced in the coil. Again, I'm telling, whenever amount of magnetic flux linked with the coil changes, an EMF is induced in the coil. So magnetic flux changes produce the induced EMF in the coil, right? Okay, and see this, the direction of current induced is given by Fleming's right hand rule. So the direction of current explained by Fleming's right hand rule. So what is Fleming's right hand rule? Please remember the Fleming's right hand rule. See this again, I'm telling, listen. In Fleming's right hand rule, thumb finger, forefinger, middle finger are mutually perpendicular to each other, right? And thumb finger represent that force or motion of conductor, and the fourth finger represent the magnetic field, direction of magnetic field, and the middle finger, it gives the direction of induced current. Which current? Induced current. Okay, students, which current? induced current. Okay, right. So this is the principle of AC generator. Okay, students, right. Now come to the components in AC generator. The AC generator has some components. The components are: one is field. Field is nothing but magnetic field. The next one is armature. Armature is a coil winding. Okay, and next is prime mover and rotor, stator, and slip rings. Yes, so these are the components in AC generator. Okay, students. Yes, right. See, in our book, yes, the components given. See, this is the stator. It consists of coil. Okay, in a winding. Next, rotor. So this is the rotor inside this coil, and this is the slip rings. Okay, now come to that alternator. So this is the alternator, right? That is generator. Okay, students, and this the brush box. There is a small brush attached to the coil, that's why brush box. And this is nothing but slip rings. These two ring is nothing but slip ring. It is attached to the coil, and this is also slip ring. Okay, students, right? This is that generator. Okay, so these are the parts. So stator, rotor, brush box, and slip rings, and armature. Okay, students, right? Okay, now there is a note. See this: alternating EMF is generated by rotating a coil in a magnetic field. The generated by rotating a coil in a magnetic field, or by rotating a magnetic field within a stationary coil. Okay, there are two methods. The first method is used for small AC generators, while the second method is employed for large AC generators. Yes, and the rotating field method is the one which most used in power station. So first method is commonly used method. Okay, rotating magnetic field. So the coil is stationary, the magnetic field only is rotated. Okay, students, right? Okay, now come to the construction of AC generator. Okay, so what is the construction? See this: alternator consists of two major parts. Namely stator and rotor. Okay, so two parts, right? Next, as their names suggest, stator is stationary while rotor rotates inside the stator. Okay, so the stator is stationary, rotor only rotates. Okay, right. See, this is fixed, this only rotates. Okay, and in any standard construction of commercial alternators, the armature winding is mounted on stator and the field magnet on the rotor. Okay, students, right? Okay, yes, briefly I'll explain with the help of these four major parts. Okay, the first one is the coil is nothing but armature. Which one? Armature. Okay, see the first one, A rectangular coil is ABCD. That is, if you are taking that coil ABCD rectangular coil, a rectangular coil ABCD consists of a large number of turns. Of copper bound over a shaft iron core is called armature. Okay. A rectangular coil consists of large number of turns of copper wound over a shaft iron core called armature. Okay, and the shaft iron core is used to increase the magnetic flux. The iron core is used to increase the magnetic flux. That's why they used copper. Okay, next, magnetic field. That is field, I explained no, that field is nothing but magnetic field. What is magnetic field? It is usually a permanent sponge magnet having concave pulses. Okay, so the surface going to inverse, that is the concave. Okay, again I'm telling, it is usually a permanent sponge magnet having concave poles. The armature is rotated of a magnet so that axis of the armature is perpendicular to the magnetic field lines. The armature is perpendicular to the magnetic field lines, so that is nothing but perpendicular to magnetic field. Okay students, right? Okay, and the third one is slip rings. Which one? Slip rings. See this, slip rings are the magnetic rings which are connected in the terminals of the armature. Slip rings are the magnetic rings which are connected in the terminal of armature, that is coil winding. Okay, and these rings are rotated with the coil, and these are used to draw the current from the generator. The coil are used to draw the current from the generator. Okay, okay students, right? And the next component, brushes is nothing but the brushes B1 and B2 are the just touch the slip rings. The brushes are just touch the slip rings, and they are not rotated with the coil. Yes, the brushes are not rotated with the coil. Okay, right. And these brushes leads to the output of the load resistance. The brushes only leads to the output of the load resistance. So these are the four components and construction. Okay, so what are the components? Armature, field, slip rings, and brushes. Okay students, right? Okay, see this, I'm telling now the construction. Yes, see the circuit. See, this is the north pole and south pole of the magnet. So between these, what will present? Magnetic field is present. That is, magnetic field line start from north pole to south pole. So this is the permanent magnet. Okay students, I said no, the rectangular coil. See, this is the rectangular coil. A, B, C, D. This is the rectangular coil, right? Okay, now the end of this coil is connected to slip rings, metallic rings. No, that is R1, R2 is nothing but which one? Slip rings. This slip rings rotate along with coil. Okay, yes, they attach it to the one common shaft. Okay students, now at the same time there is the brushes connected, carbon brushes B1 and B2. See, this is the B1 and B2 is connected to galvanometer. So B1 and B2 is, with the help of brushes only we are taking this output from the armature or nothing but coil. Okay, students, right? Okay, right. See, in our book is given. So these are the parts is given in our book. Okay, see this one. Alternator consists of two major parts, namely stator and rotor. Okay, so see this one. So this is the what, stator core, and this is the rectangular loop. Okay, stator has three components, namely stator frame and stator core and armature. So this is the stator core. This is the stator core, and this stator core is have small gaps, that is called as slot. Okay, and with the rectangular loop. Yes, stator core and with the loop, so like this. And third one is with the armature, that is with the coil winding. Yes, the end of the coil is connected small metal, yes, screws, that is outlet. These are the outlet terminals. So this is the core, and core with coil winding, core with coil winding, we called as stator winding. Okay, students, right? Next, rotor. Yes, see, this is that rotor is empty rotor. Now see this, the rotor contains magnetic field windings, slip rings and brushes mounted on the chain shaft. Okay, shaft is nothing but a long one. Okay, see that this is that 6-pole rotor. What are the poles? See this, 1 2 3 4 5 6. So these are the, which one, poles is north pole, south pole. North pole, south pole will be continuously changing, therefore poles is. And it has common axis, that is magnetic yoke. Okay, so this pole is surrounded by coil, that's why with magnetic field windings. See this, the gaps, the yoke, so the pole is surrounded by coil. Okay, see coils, the coils are, yes, mounted on this poles. At that end of this one is connected to the, which one, slip rings. So the axis of the coil is connected to slip ring, and with the, in the end of the coil taking the output. See this one, see, this is that output. Okay, so the one end of the coil is connected to the what, slip rings. So this setup placed inside the stator core. See this, so inside this core, stator core. Okay, okay, see that output frame is the stator, so this rotor placed inside the stator core. So these are the parts of what, generator, AC generator. Okay, students, right. Working of AC generator, working of AC generator. What is the working? See this, the coil is rotated in an anti-clockwise direction. Which direction? Anti-clockwise direction. Okay, in the first, yes, in the first half rotation, yes, the half rotation of the arm AB is moving outwards and CD is moving inwards. That means one going to move, yes, downwards, and CD face going to upwards. Okay, right. So the EMF is induced in the arm, the EMF is induced in the arm AB from A to B. So because the flux changes in the Yes, area of the coil, induced EMF produced. Therefore, AB side induced EMF produced. Okay, right. And in the arm CD from C to D, after the half rotation, yes, the CD going to which one? Moving outwards, and AB is moving inwards. Just opposite this one, right? So therefore, second half CD going to downwards and AB side going to upwards. Okay, students, right? Okay, so in this time, current is induced in the arm CD. That current from D side, D to C. Okay, okay. And in arm A, B, from B to A, from B side, the current flow from B to A. Okay, therefore in the second half rotation, the current direction is changes. So that is so in this generator, AC is produced. So the direction of current in second half rotation, current direction changed, therefore is generate the alternative current. Okay, students, right? Okay, so yes, for your understanding purpose, see this is the coil. So this is the, see this one position, and there is that another position. Okay, so this is the perpendicular position, and this is what parallel position. Okay, see this, when the coil is in vertical position, see this vertical position, no magnetic field lines are cut AB and DC. So there is no magnetic line, because magnetic lines cross from north pole to south pole. So if the coil is placed in vertical position, there is no magnetic field lines are cut, so no EMF, right? So when the coil is perpendicular to the magnetic field, there is no EMF. That means no EMF means no current flow. Okay, students, suppose while the coil rotated in the cut the magnetic field and cause changes in magnetic flux, so an EMF is induced, which case the electric current flow the circuit. So suppose if the coil like this, the magnetic flux changes. So if the coil rotated, the magnetic flux changes, so it will produce the induced EMF, then only electric current flow the circuit. Okay, students, right? You understand? Okay, and see this, the coil rotated in their phase differences. See, when the coil is in this position perpendicular, there is no EMF. That means if theta is equal to 0 degree, E is equal to 0. When the coil in this like this position pi by 2, that is parallel, when that angle is 90 pi by 2, EMF is produced maximum. Again the coil is rotated again in clockwise direction, again come to perpendicular, that is theta value is 180, there is no EMF. Again coil rotate in anti-clockwise direction. Now the coil position is 270, that is 3 by 2. It has induced EMF, that means it will produce the induced EMF. And again the coil come to the position. Now the phase is 360. At that time there is no induced EMF. So see this, the EMF values alternatively changes. So this is one positive half cycle, and this is that another negative half cycle. So alternatively changes. Okay, okay, students, right? See, and I said no phase changes, phase difference. See, this E is nothing but induced EMF, and I is nothing but induced current. Okay, now see this phase difference. If two alternative quantities of same frequency do not pass through a particular point, right? Same frequency do not pass through the particular point, and say 0 point, if the same direction at the same instant, they are said to move have phase difference. Therefore the angle between 0 points is the angle of phase difference. Please underline, the angle between 0 points is the angle of phase difference. Okay, see from the graph shown above, the phase difference between the E and I is given by pi. So the angle between the induced EMF and the current, induced current, is nothing but phase difference. The phase difference denoted by pi. So please note it down, phase difference is pi. Okay students, right? Okay, advantages of AC current. Now come to the advantages of AC current. Okay, right, see the advantages. And these generators are generally maintenance free because of absence of brushes. Okay, and easily step up and step down through transformers. Okay, and transmission link size might be thinner because of step up feature, right? And size of the generator relatively smaller than DC machine. The generator size is smaller than the DC machine. Okay, and next, losses are relatively less than DC machine. Losses are less than DC machine. Okay, and these generators breakers are relatively smaller than DC breakers. The AC generator breakers is smaller than DC breakers. Okay students, so these are the advantages of AC generator. Okay students, right. Next, applications of AC generator. Applications of AC generator. See the applications. The first one is hybrid electric vehicles, that is HEV drive systems. So in this drive systems, AC generators are used, and it is used in automotive starter generators. We called self motor, right? Okay, next, aircraft auxiliary power generation. So aircraft auxiliary power generation. So for power generation and aircraft, they are using AC generators. Okay, now and the next, wind generators. Okay, for winds they are using generators. And next, high speed gas turbine generators. High speed gas turbine generators. So these are the applications of AC generators. The AC generators are used in these areas. Okay students, right. Students, today class is over. Okay, okay students, so please go through the AC generator topic. It's a theoretical topic, so please just go through the topics once. Okay students, right. Okay, right, so we'll see on next video. Okay students, right, thank you.